Hello and welcome back to the course on Introduction to Solid-State Physics. In the last class we have discussed about the reduced zone scheme for a free electron. We had only introduced the effect of periodicity of the potential. We had not taken into account the strength of the potential. Now let us look a little more realistic model and let us look into the strength of the potential, because that is the actual case. In a one-dimensional lattice, we are having these nuclei which are periodically arranged, and each of these nuclei are having they exert certain potential. Suppose this is the nucleus. So around the nucleus we are having such kind of Coulombic potential, and if the nuclei are arranged in a periodic manner, this is how the net potential will appear, and inside this the electron wave is moving. So this is the electron wave. So in this periodic potential the electron wave is moving, and this model was first of all simplified by Kronig-Penny, and famously it is also called as the Kronig-Penny model. So in this lecture we are going to be a little bit more realistic, and we are going to still stick to the nearly free electron model. That means we are going to solve the Schrödinger equation for the Bloch electrons. That means the electron is experiencing the effective potential due to all other electrons and the nuclei, and only we are going to take into the strength of the potential, which is periodic in nature. So this kind of actual potential was approximated by Kronig and Penny into a rectangular form. Now instead of assuming this kind of Coulombic form of the, that is 1 by r form, we are assuming a rectangular potential barrier which is periodic in nature, and for simplicity we are assuming only in the case of one dimension. So this is a one dimension potential and it is periodic, and the form of the potential is rectangular in nature. Now let us look at this particular graphical scheme of the potential that the electron is experiencing inside a crystal. In the region 1, the electron is not experiencing any potential and the width of this region is A, whereas in the region 2 the strength of the potential is V naught and the width of the potential is B, and this particular structure is getting repeated in the entire lattice. So the periodicity of the crystal in this case will be A plus B. So this is A, so this one is A plus B, which is being repeated periodically to generate the entire crystal. So now let us define the potential in these two regions. That is, in the region 0 less than x less than A, we are not having any kind of potential, whereas in the region 2, that is in this region in between minus B less than x less than 0, the potential is V naught. And let us write down the Schrödinger equation in these two regions. So obviously in the region 1 it will be the Schrödinger equation for a free particle, that is d square psi 1 by dx square plus 2me by h cross square psi 1x is equal to 0. In this case the potential is 0, so that's why it takes the form of a free particle. On the other hand, so let us first simplify it and look at the solution of it. So this constant can be taken as beta square, that is 2me by h cross square. Now the equation becomes d square psi 1x by dx square plus beta square psi 1x is equal to 0, where beta is root over of 2me by h cross square. We are well acquainted with this kind of solution because we know the plane wave solution for a free particle. Already we have seen this kind of solution in the free electron theory. So psi 1 x can be written with the help of two unknown coefficients a and b, that is a into e to the power I beta x plus b into e to the power minus I beta x. So this is the solution of the wave function in the region 1, where the electron wave is not experiencing any kind of potential. Now let us focus on the second region. In the second region, the potential is V naught, so it will be 2m by h cross square E minus B naught psi 2x is equal to 0. Remember here the wave function psi is different from the region 1. Now we are representing it with psi 2x. Now this particular constant can be written in terms of alpha, which is root over of 2m by h cross square into V naught minus E, so that this particular form can be written as minus of alpha square psi 2x. Now again, this kind of equations are very common in physics. The solution for this can be written in terms of the exponential function, either increasing or decreasing form, that is the unknown coefficient c e to the power alpha x plus d e to the power minus alpha x, where alpha is root over of 2m by h cross square b naught minus e. Now we can see that from the region 1 wave function is psi 1, and we are having the unknown coefficients a and b, and beta depends on energy of the electron, whereas in the region 2 where the electron is experiencing the potential V naught, in this case we are having the unknown coefficients c and d, and alpha depends on the strength of the potential and energy of the electron. So these are the parameters which we are going to deal with. Now we are having four unknown coefficients a, b, c and d, and the unknown coefficients can be evaluated by applying the boundary conditions. Now let us go back once again to the diagram here. So let me erase the ink here. So the wave function, this is psi 1 and this is psi 2, and at this boundary, that is x equal to 0, the wave function must be continuous. That is one of the properties, basic properties of the function to be qualified as a wave function. So psi 1 must be equal to psi 2 at x equal to 0. Similarly, the first spatial derivative of psi 1 and psi 2 also they will be the same at x equal to 0. Psi 1 must be equal to psi 2, and d psi 1 by dx also should be equal to d psi 2 by dx at x equal to 0. That is what is the first periodic boundary condition. First boundary condition, you can write it like this. The boundary condition at x equal to 0, so that psi 1 at x equal to 0 will be equal to psi 2 at x equal to 0. Similarly, the first spatial derivative of psi 1 and psi 2 with respect to x at x equal to 0 will also be the same, because this is coming from the basic conditions that is imposed on the wave function. Now the second condition that you are applying here is the condition that we got it from the Bloch's theorem. If you recollect, if we are having a periodic potential, that is Vr, if Vr is equal to Vr plus T, then by applying the Bloch's theorem, we had seen that psi k r plus T can be written as e to the power I k dot T psi k r. Since it is a case of one dimension, In this case, the vector t is simply a plus b. So we can apply this particular expression in the present context. So if you do that, in this case we are having Vx plus a plus b is equal to Vx. So psi k x plus a plus b will be equal to e to the power I k a plus b psi k x. Since it is one dimension, so it will be simply e to the power I k a plus b, because t is a vector in 3 dimension, but along the x axis it is having only 1 dimension, so it is a scalar. We are having this particular expression from the Bloch's theorem. Now we can apply this at the boundary condition for psi 1 and psi 2. If we do that at the points x equal to a and at x equal to minus b, because the periodicity is a plus b. Let me go back to the initial diagram here. So the wave function is being repeated from here to here. So if you go from one unit cell from here to here, then we will have the same wave function with a phase factor of e to the power I k a plus b, and the same thing will hold good for the first derivative of the wave function. And in this region the wave function is psi 2, and at the point a the wave function is psi 1. At the point b, at the position minus b, wave function is psi 2, and at the position x equal to a the wave function is psi 1. Now let us impose this condition, which is obtained from the Bloch's theorem, and let us see what we are getting. That is psi 1 x at x equal to a will be equal to e to the power I k a plus b psi 2 x at x equal to minus b. Similarly, the first spatial derivative, that is delta psi 1 x by delta x, will be equal to the same phase factor e to the power I k a plus b delta psi 2 x by delta x at x equal to minus b, because the same wave function is going to be repeated at x equal to a and at minus b with a phase factor of e to the power I k a plus b is coming from the Bloch's theorem. Now we are having the 4 boundary conditions. One is the continuity condition at x equal to 0, and other is a combination of the Bloch's theorem and the continuity condition at x equal to a and x equal to minus b. So if we apply this 4 boundary condition, we are going to get these 4 equations, and now we are having the 4 unknown coefficients. Now let us see what are these equations by taking these conditions. So the first condition will give you a plus b is equal to c plus d. So this we are going to get from psi 1 x at x equal to 0 is equal to psi 2 x at x equal to 0. Similarly, if you take the first spatial derivative with respect to x, then we can obtain this condition, that is I beta a minus b is equal to alpha into c minus d. And from the Bloch's theorem, we are going to get c into e to the power minus alpha b plus d into e to the power alpha b is equal to e to the power minus I k a plus b into a into e to the power I beta a plus b into e to the power minus I beta a. Remember, here we are comparing at x equal to a and minus b, that's why this phase factor is coming here. Similarly, for the Last boundary condition, the first derivative of the wave function at x equal to a and at x equal to minus b will get this particular condition. Now we can obtain a solution to this set of equations and which is not of our interest. Our interest is to know when the solution will exist. The trivial solution is that all ABCD are 0, but we are not interested in that. We are interested only in the non-trivial solution. And under what condition the non-trivial solution will exist? For that, the associated determinant of this constant coefficients, parameters multiplied with this constant coefficients, has to be 0. That means this particular determinant will be 0, then only this non-trivial solution will exist. And this determinant we are going to get from here. The constant multiplied with a is 1, 1, 1, 1. So it will be written as a plus b minus c minus d is equal to 0. So the coefficient is 1, 1, minus 1, minus 1. Similarly, here also we can bring out all the coefficients into the left hand side. So I beta a minus b minus alpha into c minus d is equal to 0. So like that we can collect all the coefficients and a 4 cross 4 determinant will come. So if you evaluate it, then we can get this. If you expand the determinant, then we are going to get this particular equation, that is alpha square minus beta square by 2 alpha b sine hyperbolic alpha b plus sine beta a plus cos hyperbolic alpha b into cos beta a is equal to cos k a plus b, cos k a plus b. So here the hyperbolic functions are there on the left hand side and the cosine function is there on the right hand side. That means you can plot a graph for this particular left hand side, and this left hand side should only exist between plus minus 1. So the boundary of the left hand side is limited by this right hand side of this particular equation. That means only for those values of the function which lies between plus 1 and minus 1, the particular equation will be physically valid. For all other values it will be not allowed. Now let us look into it little bit more closely under certain extreme approximations. As I told, the right hand side is going to lie between plus 1 and minus 1. When it is plus 1, that means cos k a plus b is equal to 1, that means k is equal to 0. And when it is minus 1, k will be equal to plus minus pi by a plus b. And this is the first Brillouin zone of the lattice under consideration. That means from minus pi by a plus b to plus pi by a plus b. And at k equal to 0, we are having the one of the lattice points. Now the value of the energy for which the left hand side lies inside this region, that is between plus 1 and minus 1, those energy states are allowed. If for a particular energy value this function is lying outside plus or minus 1, then they are not allowed, and those energy levels are called as the forbidden energy levels. So this is the origin of the forbidden bands in the solids. Let me repeat. So for the value of energy of the electron for which the left hand side function, this one, is going to lie between plus 1 and minus 1, only those energy values are allowed, whereas if it is lying outside +1 and -1 region, then those energy values are not allowed, or those are the forbidden energy levels. Now let us take some extreme examples. Let us assume that the width of the potential is very small and the strength of the potential is very high. That means we are going to almost consider a Drack Delta kind of function. So the width B is almost 0. It is very small width, and the strength of the potential is very high, very low. Now these are separated through a distance of A. So along the distance A, there is no potential experienced by the electron. Now under this extreme condition, we can rewrite the above equation. This equation can be rewritten when B tends to 0 and V naught tends to infinity. Remember here alpha is what? Alpha is root over of 2m by h cross square V naught minus E, and beta is root over of 2me by h cross square. So beta is directly related with the energy of the electron. Under this condition, we can rewrite that equation, and this will be the form of the equation. That is, now we can write this alpha square minus beta square by 2 sine hyperbolic alpha b as, so this will be reduced to m v naught by h cross square alpha b. I am not going into the details of the mathematics, so we can cross check it, and it will be equal to, if we rearrange the terms, we can write it as ma by h cross square alpha by a b v naught, and we can replace this ma by h cross square b v naught with another constant p, so that we can write this left hand side as p into alpha by a. That is, the first term on the left hand side can be written as p into alpha by a under this extreme approximation. Now our equation will reduce to p by a beta into sine beta a plus cos beta a is equal to cos k a. Now the right hand side, since b tends to 0, so it will be simply cos k a, and the second term is going to remain the same except the b term here, so it will be cos beta a. Now it is relatively easy to plot this function. So again, this is bounded between the values +1 and -1. Now let us see, if we plot the left hand side with respect to the beta a, this is how the function will look like. So we are plotting this LHS. The variable here is beta a. With respect to beta a, this function is being plotted, and this is what is the form of the plot. So beta a can take the values 0, 2 pi, 6 pi, these are the 4 pi, here are the values for beta a. So beta, once again let me write it, it is beta is equal to root over of 2me by h cross square, and a is the width of the region in which there is no potential, where the energy is completely E. So beta is having a dimension of 1 by length, and a is having a dimension of length. So this is how the beta a can be represented. Now if we carefully look into this graph, we can see that the regions which are inside this -1 and +1, these are the allowed regions. So this is the region. So this particular region, this region, this region, these are the allowed regions, and in between these two allowed regions, certain regions are there which is not allowed. These are the forbidden regions. This is how we can explain the existence of forbidden band or the band gap in a insulator or a semiconductor. Now let us look at this graph little bit more carefully. When the value of beta A, with the increase in the value of beta A, basically we are going to increase the energy of the electron. With increase in beta A, what is happening? The width of the allowed bands, so this one is little narrow, this one is little wider, this one is more wider, this is much more wide. We can see that the width of the the width of the allowed band is increasing with increase in beta A, or with increase in the energy of the electron. When E becomes very large compared to the strength of the potential in which the electron is moving, the width of the allowed band is very large. So we can say that it is almost a continuum region when the energy of the electron is very large. Similarly, if we consider the other extreme, when the potential is very large, when V0 is very large compared to the energy of the electron, the width of the allowed band is almost like a single line. So that means we can talk about the discrete energy levels when the potential is very large, or for a single atom or a molecule where there are no free electrons. In that case, we can talk about the existence of discrete energy levels. So we can take two extreme examples. In one case, it is the behavior of the metals, where it is a continuum of the allowed energy levels. In other case, we are having the discrete allowed energy levels where the potential is very large compared to the energy of the electron. This is what has been discussed here. As V0 is very small, we can see that we are having a continuous allowed state of energy. Under this condition, P will become 0, and that is the case for the metals. And the width of the allowed energy bands increases with the increase in the energy, and that of the forbidden bands decreases with increase in the energy. Also, we can see the emergence of the energy band gap at the boundary of the Brillouin zone. In all the boundaries, we can see that the electron wave is being strongly reflected, and because of which there is an existence of the band gap. Let us look at it more carefully in the band diagram. This is the band diagram for the electron moving inside the crystal under a periodic potential of certain strength. This is our fast Brillouin zone between minus pi by a plus b to plus pi by a plus b. These are the higher order Brillouin zones boundaries, and whenever we are facing a boundary for the Brillouin zone, we are having the emergence of the band gap. So these are the allowed bands. Let me change the color here. These are the allowed bands. The moment it sees one Brillouin zone boundary, there is a forbidden band here. Then again, these are the allowed bands. Then again, it is going to see another Brillouin zone boundary. There is a band gap here. And like this, the width of the forbidden band keeps on increasing with increase in the Brillouin zone. For higher order Brillouin zone, the width of the forbidden band is more and more. So here, these are the allowed bands. And then comes the forbidden band. This is the again allowed band, then comes the forbidden band. Whenever it encounters one brilliant zone boundary, there is the emergence of the forbidden gap, and the forbidden band width increases with higher order brilliant zone. Now we can apply the same transformation which we had used earlier, that is k prime sg is equal to k, to bring back all the wave vectors inside the fast brilliant zone, which is called as the reduced zone scheme. Here we can see that this portion has been brought back here. Similarly, this portion has been brought back here. So this portion is here and this portion is here. In this manner we can bring back all the portions of the EK band diagram which is lying outside the fast brilliant zone inside the fast brilliant zone using the reduced zone scheme. Now let us summarize. We saw that by applying a periodic potential of certain strength, we can see the emergence of the energy band gap, and the width of the energy of the forbidden band keeps on increasing with increase in the high brilliant zone, increase in the order of the brilliant zone. And with this we can distinguish between the metals and the semiconductors or the insulators. Basic outcome of the Kronig-Penny model, which describes the motion of electrons inside a periodic potential, is the distinction between the metals and the insulators. In case of metals, the energy of the electrons is very large compared to the potential imposed by the ions. That's why we can apply the free electron model, and we saw that in that case the allowed bands are completely continuum and the width of the allowed band is very large, whereas if V0 is very large, under which E is very small compared to V0, in that case the insulators exist, and under extreme case when V0 tends to infinity, we see the existence of discrete energy levels. When E is very small compared to V0, we can see the emergence of the energy band gap, which is the case in case of the semiconductors and insulators. And when V0 is very large, for example in the case of an atom or a molecule or a cluster of molecules, in that case we can see the existence of the isolated energy levels. It is just like a particle is confined inside a box. So with this we will conclude today's lecture. In the next lecture we will be trying to interpret the energy band diagram. For example, what is the slope and the curvature of this EK energy band diagram correspond to. It will give us an idea about the motion of the electron inside the solid, about the speed of the electron and about the effective mass of the electron, which will be doing it in our next lecture. Thank you.